To verify the calculation of secondary short circuit amps or SCA on a 75 kVA transformer with a voltage rating of 480 volts to 280 to 120 volts, three-phase, with an impedance of 5.5%, we can use the point-to-point method. The initial condition is given as 19,963 amps of SCA at the primary, and the calculated secondary SCA is 3,501 amps. The formula for calculating the secondary SCA using the point-to-point method is as follows: secondary SCA equals primary SCA multiplied by secondary voltage divided by primary voltage. Using the supplied numbers in this scenario, secondary SCA equals 19,963 amps multiplied by 208 volts divided by 480 volts. The result of the calculation is 3,501 amps. Therefore, the secondary SCA calculation of 3,501 amps is correct based on the provided primary SCA and transformer voltage ratings. It is important to understand the underlying principles and assumptions of the point-to-point method to ensure accurate application and interpretation of the results. Firstly, the point-to-point method is a simplified approach for calculating short-circuit currents in electrical power systems. It assumes that the voltage drop between the source and the point of fault is negligible, which may not always be the case, especially in systems with long cable runs or high impedance. Secondly, the point-to-point method relies on the availability of accurate impedance data for all components in the circuit, including transformers, cables, and protective devices. Inaccurate impedance data can lead to significant errors in the calculated short-circuit currents. Thirdly, the point-to-point method does not account for the effects of motor contribution, which can significantly increase the short-circuit current, especially in industrial facilities with a large number of motors. Fourthly, the impedance of the transformer plays a critical role in determining the magnitude of the short-circuit current. The transformer impedance limits the current flow during a short circuit, protecting the transformer and other equipment from damage. A higher transformer impedance will result in a lower short-circuit current, while a lower transformer impedance will result in a higher short-circuit current. Fifthly, the transformer kVA rating also affects the short-circuit current. A larger kVA rating means the transformer can supply more current during a short circuit. However, the transformer impedance is the primary factor limiting the short-circuit current. Sixthly, the primary voltage and secondary voltage of the transformer are used in the calculation of the secondary short-circuit current from the primary short-circuit current. The voltage ratio determines the turns ratio of the transformer, which affects the current transformation. Seventhly, the 5.5% impedance value represents the percentage of the transformer's rated voltage that is required to circulate full load current during a short-circuit condition. This value is crucial for determining the short-circuit current at the secondary terminals of the transformer. Eighthly, the calculated short-circuit current is used to select appropriate overcurrent protection devices, such as fuses and circuit breakers. The interrupting rating of these devices must be greater than the calculated short-circuit current to ensure that they can safely clear fault. Ninthly, the available short-circuit current at the secondary terminals of the transformer is also used to determine the required short-circuit current rating of downstream equipment, such as panel boards, switchboards, and motor control centers. This equipment must be able to withstand the mechanical and thermal stresses caused by the high fault current. Tenthly, this short-circuit current calculation should be performed by a qualified electrical engineer or technician who is familiar with the relevant standards and codes, such as the National Electrical Code, or NEC. Proper grounding is essential for electrical safety and to minimize the risk of electric shock. Grounding provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices to quickly clear the fault. The grounding system should be designed and installed in accordance with the NEC. Bonding is the process of connecting all metallic parts of the electrical system together to create a common ground. This includes metal conduits, enclosures, and equipment frames. Bonding helps to equalize the voltage potential between different parts of the system, reducing the risk of electric shock. Overcurrent protection devices, such as fuses and circuit breakers, are used to protect electrical circuits from overloads and short circuits. These devices are designed to interrupt the flow of current when it exceeds a predetermined level. The interrupting rating of overcurrent protection devices must be greater than the available short circuit current at the point of installation. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning strikes or other transient events. SPD divert the surge current to ground, preventing it from damaging sensitive electronic components. SPD should be installed at the service entrance and at downstream panels to provide comprehensive surge protection. Arc flash is a dangerous phenomenon that can occur when a short circuit creates a high-energy electrical arc. Arc flash can cause severe burns, blindness, and even death. Electrical workers should wear appropriate personal protective equipment, or PPE, when working on or near energized electrical equipment to protect themselves from arc flash hazards. The NEC provides guidance on the selection and use of PPE for arc flash protection. Lockout/tagout procedures are used to ensure that electrical equipment is de-energized before any work is performed on it. Lockout/tagout involves placing a lock and tag on the disconnecting means to prevent the equipment from being accidentally energized. Only authorized personnel should be allowed to remove locks and tags. Electrical safety audits should be conducted regularly to identify potential hazards and ensure that electrical safety procedures are being followed. Audits should be performed by qualified personnel who are knowledgeable about electrical safety standards and codes. Electrical safety training should be provided to all employees who work on or near electrical equipment. Training should cover topics such as electrical hazards, safe work practices, and the use of PPE. Training should be updated regularly to reflect changes in standards and codes. Regular maintenance and inspection of electrical equipment is essential to ensure its safe and reliable operation. Maintenance should include tasks such as tightening connections, inspecting insulation, and testing protective devices. Inspections should be performed by qualified personnel who are trained to identify potential problems. Electrical drawings and documentation should be kept up to date to reflect any changes to the electrical system. This includes single-line diagrams, panel schedules, and equipment manuals. Accurate documentation is essential for troubleshooting and maintenance. Power quality is a measure of the quality of the voltage and current in an electrical system. Poor power quality can cause equipment malfunctions, premature failure, and increased energy consumption. Power quality problems can be caused by factors such as harmonics, voltage sags, and transients. Power factor is a measure of the efficiency of an electrical system. A low power factor indicates that the system is not using energy efficiently. Power factor correction can be achieved by installing capacitors to offset the inductive load. Energy efficiency is the practice of using less energy to perform the same task. Energy-efficient equipment and practices can save money and reduce environmental impact. Energy audits can be used to identify opportunities to improve energy efficiency. Renewable energy sources, such as solar and wind power, can be used to generate electricity. Renewable energy sources are environmentally friendly and can reduce reliance on fossil fuels. The NEC provides guidance on the installation of renewable energy systems. Smart grids are electrical grids that use advanced technologies to improve efficiency, reliability, and security. Smart grids can monitor and control the flow of electricity in real time, allowing for better management of the electrical system. The Internet of Things, or IoT, is a network of interconnected devices that can communicate and exchange data. The IoT is being used in the electrical industry for applications such as remote monitoring and control, predictive maintenance, and energy management. Cybersecurity is the protection of computer systems and networks from unauthorized access, use, disclosure, disruption, modification, or destruction. Cybersecurity is essential for protecting critical infrastructure, such as the electrical grid, from cyberattacks. Artificial intelligence, or AI, is the ability of computer systems to perform tasks that typically require human intelligence, such as learning, problem-solving, and decision-making. AI is being used in the electrical industry for applications such as fault detection, predictive maintenance, and grid optimization. Blockchain is a distributed ledger technology that allows for secure and transparent transactions. Blockchain is being used in the electrical industry for applications such as energy trading, supply chain management, and smart contracts. The future of the electrical industry is being shaped by technological advancements, increasing demand for electricity, and growing concerns about climate change. The industry is evolving to become more efficient, reliable, and sustainable. The calculation of secondary short-circuit amps on a transformer is a fundamental aspect of electrical system design and safety. Accurate calculation and proper application of the results are essential for protecting equipment and personnel from the hazards of short circuits.